Hi, this is George Arrington, and I want to present a problem that involves both mathematics and physics, and I hope you will find very interesting. So here's the statement of the problem. An elastic ball is dropped from a particular height onto a hard flat surface, and we'll say that this is a perfectly elastic ball and no energy is lost through friction or heat or air resistance or anything like that. And we'll also say that this bounces only vertically up and down. It does not go from side to side. And also it will go up each time it bounces to a particular fraction of the previous height. So for instance, on this one, if it starts at 16 meters, let's say that it bounces up 1/2 of the previous height. So it's going to bounce up 8 meters. It then falls back to the surface and bounces up again, and this time it will bounce up that same fraction. So for this problem, we're going to say that it bounces up the same fraction of the previous height. So now the previous height is 8 meters, so it's going to bounce up 4 meters. And again, for the purposes of this problem, we assume that the fraction is the same as the first, and so on and so on. This is not true in a real-world problem, but it's a good first approximation. Things like friction and air resistance happen in real-world problems, but we'll say that this is a very elastic bouncing ball. The bouncing will then continue each time, so it bounced once, it bounces twice, and so forth, and each time it bounces, it will bounce the same fraction of the previous height. Now here's where it gets interesting. If the bouncing continues with smaller and smaller bounces over an infinite number of times, and understand that infinity is a lot bigger than a million, it's a lot bigger than a trillion, it's bigger than any number that you can name. If it bounces over an infinite number of times, can we write an expression to calculate the total vertical distance traveled by the ball? So it goes up and down and up and down. What is the total distance that it travels over this infinite number of bounces? So consider the following. So the ball starts up here at some height, and I'll use a dotted line to indicate that initial height. And it falls down and hits the surface and bounces back up to another particular height. In this case, let's say that it started at 16 meters and it bounces back up to half of the original height, which is 8 meters. But then what goes up must come down. It falls back down and bounces up to half of the previous height. Half of 8 is 4 meters, which we'll say is right about there. And this continues on and on forever. So now let's put some variables in here, some values in here, and we'll say that it starts at a height called h1, it drops down, it goes up to h2, so some other height. We're not specifying the numbers here. But then it falls back down the same height, h2, because again, what goes up must come down, and that h2 is the same as that h2. Okay, the going up and the coming down is the same h2. Likewise, for the other bounces, it goes up, in this case we'll say h3, it comes back down h3. It goes up h4, it comes back down h4. So let's write this out in an equation. D, we'll say, is the total distance that it travels, is the initial drop, h1, plus h2, that's where it bounces back up the first time, but then it falls back down h2, so we have to add in another h2. And likewise, we would do the same thing for h3, up and down, and h4 up and h4 down. And then we continue that forever. Now we can simplify this by combining some like terms. So we'll say h1 plus 2h2, h2 plus h2 is 2h2, plus 2h3 plus 2h4 plus 2h5 plus 2h6, and so on and so on and so on. So now let's take off those subscripts of 1, 2, 3, and 4, and let's define everything in terms of just the initial drop h. Let's assume that we're going to have another letter, we'll call it r, and this is the fraction of the previous height that the ball bounces. And we'll assume that this is between 0 and 1. If it's 0, just as an aside, if it's 0, then the ball won't bounce at all. It'll just thud onto the ground and stop there. If it's 1, it will always bounce up to the same height. And if you do that an infinite number of times, that will certainly go to infinity. So we're going to assume that it's some fraction between 0 and 1, not equal to either of those. By the way, I'm using r because r stands for ratio, and this is going to be a common ratio. We'll see that term later. So when it bounces back up the first time, it's going to be r times that original height. So for instance, if we say that the initial height was 16 and r is equal to 1/2, then 1/2 times 16 is 8. So likewise, it has to fall back down the same r times h. Now the next bounce, we multiply it again by r. So in this case, it's going to be r times h, or r squared times h, up and down. And you can probably guess that the next one will be r times r squared times h, or r cubed times h, and back down r cubed times h. And the succeeding terms will be r to the 4th times h, r to the 5th times h, and so forth. So we can write this now in terms of just h and r by saying the total distance d is equal to h, the initial drop, plus 2r, and by the way, that r is to the first power. We'll see that later, but 2r times h plus 2r to the second power times h plus 2r to the third power times h, and so on and so on. Now let's do an example, and we'll do the example that I was talking about before. The ball is initially dropped from a height of 16 meters. Each time it bounces up 1/2 of the previous height. What will the total distance be? So here's how we set the problem up. We start with the initial drop of 16 meters down. Then it's going to bounce back up 8 meters and then fall back down 8 meters. And then it's going to bounce back up 4 meters, that's half of 8, and down 4 meters. And up 2 meters and down 2 meters, and so on and so on and so on. The same pattern, taking half of the previous height each time, up and then down. Now let's extend this a little bit. We'll add more terms and rewrite it in the following way, putting in some actual values. The total distance d is equal to 16 meters plus 2 times 8 meters plus 2 times 4 meters plus 2 times 2 meters plus 2 times 1 meter plus 2 times 1/2 meter plus 2 times 1/4 meter plus 2 times 1/8 meter, and so on and so on and so on. And you'll notice that the fractions are getting smaller and smaller and smaller. And now if we actually work these problems out, do the multiplication, we get 16 meters plus 16 meters plus 8 meters plus 4 meters plus 2 meters plus 1 meter plus 1/2 meter plus 1/4 meter, and so on. So here we have the initial drop and then 7 additional ups and downs. So the question is, will this infinite sum, and again we're adding an infinite number of terms, an infinity of terms, a huge number, more than you could ever count. Will this infinite sum of terms continue to grow without limit, or will it get closer and closer to a particular number? Will it converge to some finite number? Well, let's find out. To do this, what I'm going to do is I'm going to do an experiment, or do this experiment, by using a Microsoft Excel spreadsheet. And here's what I got. The first column is the step number. 0 is the initial drop, 1 is the first bounce, 2 is the second bounce, and so forth. The second column is the vertical distance. So we start with 16. We take half of that each time as we go down. Now, for the third column, we double each of those numbers in the second column, except for the first one, because there was only one of those. And then we get a running total of how much the total distance will be. So starting with the initial drop, it's dropped 16 meters. And so under the running total in the first row, we have 16 meters. Now, in the second row, we add that 16 meters to the 16 meters for the first bounce, the 8 up and 8 down, and we get 16 plus 16 is 32. For the second bounce, we add on 8, and 32 plus 8 gives us 40. And so forth and so on. We continue that process all the way down. Now, for the previous example on the previous slide, we only went up to here. We only went up to 7 bounces. And so at that point, the total distance traveled by the ball is 47.75 meters. But we could keep going like this, and the nice thing about Excel is that you can extend the computations as far as you want to go. And so I did this down to 12 bounces, and you'll see that the value that I got was 47.99219. Well, if we look at the trend of these numbers, it looks like it's trending towards a particular value. It seems to be getting closer and closer to 48. Isn't that interesting? So the question is, can this problem be generalized to put in any values for the initial height and the common ratio, or the fraction that it bounces? So we're going to assume that all we need are those two things, the initial height and the fraction of the previous height, which we could also call the common ratio. Using these values, we can write the expression as follows. H plus 2h times the common ratio to the first power, and there I'm using the actual exponent r to the first power, which is the same thing as just r, plus 2h to the second power, or 2h squared, plus 2h cubed, plus 2h to the fourth power, and so on and so on and so on. So there's the initial drop, there's the first bounce, there's the second bounce, and those bounces include both up and down. That's what the 2 times in front means. There's the third bounce, fourth bounce. So next we're going to do something a little bit strange. We're going to use this equivalence, and I need to explain this. H is the same thing as negative h plus 2 times h times r to the 0 power. What the heck does that mean? Well, what that means is if we take 2 times h and subtract an h from it, if we take 2 h's and subtract 1 h from it, we'll end up with an h. So that's what the left-hand side says. It's like saying if you have 2 apples and you take away 1 apple, you have 1 apple. So that's the simple part of it. And the r to the 0 power there, anything other than 0 raised to the 0 power is equal to 1. So that's the same thing as saying 2 times h times r to the 0 power is the same thing as 2 times h. The rationale for this is going to be apparent in just a little while. Now, the preceding expression may now be written using this unusual equivalence we're going to substitute for the h at the beginning, that initial drop, and write it this way. D is equal to that strange thing, negative h plus 2h times r to the 0 power, plus the rest of it that we did previously. Now, the interesting thing about this, the way I've written it, is that it can now be written in a, this infinite expression can be written in a very short form that looks like this. D is equal to the same negative h that we see above there, but now all of the other terms can be represented by this notation. That funny symbol in the middle there is called sigma. It's a capital Greek letter S. Kind of looks like an E, but it's the letter S, capital S in Greek, which means sigma. And in engineering and mathematics, we use that to indicate the summation of a set of numbers or a series of numbers. And in this case, we're saying sum where I is equal to starting at 0 and going to infinity. So I will be 0 and then 1 and then 2 and then 3 and so forth. And we add all of those terms up. And the terms are 2 times h times r to the I power. So the first time through it will be 2h r to the 0, which you see above. And that's the reason I did that equivalence at the top. Plus 2 times h to the first power, plus 2 times h to the second power, plus, again I'm saying plus because we're summing up all of these things, and that's what the Greek letter sigma means. So let's just concentrate on this part for just a moment. What we look at, when we look at that, when mathematicians look at that, they say, oh, this looks like what's called a geometric series. And a geometric series can be written as this. The summation from 0 to infinity of a times r to the I power. And in this case, a represents some constant value, something that does not change. And then it's multiplied by some common ratio raised to some power, and that power is the thing that is changing within the summation. So this is called a geometric series. Now the cool thing about this geometric series we see on the next slide. If you do this, and the common ratio is between 0 and 1, it's not 0, it's not 1, but it's somewhere in between, some 0 point something, then a very interesting result happens. This infinite summation of all of these terms turns out to be this. A, the constant, over 1 minus r. There's no infinities in there, there's no exponents, it's just simply the constant divided by 1 minus the common ratio, which is a very interesting result. Now there is a proof for this, but I'm not going to do it here on this presentation. So using this fact in the previous expression for our total distance, we can say that the total distance is our negative h plus the summation from I equals 0 to infinity of 2 times h to times r to the I power. And substituting into our geometric series expression, we simply say negative h plus 2h, that would be our constant, the thing that does not change, divided by 1 minus r. So it's a really simple expression for something that's bouncing up and down an infinite number of times. But let's do some rearranging to make the formula look a little more neater. We'll start with this. We'll take the negative h and get a common denominator of 1 minus r. So we multiply top and bottom by 1 minus r. We'll then distribute the negative h into the parentheses there and add the two fractions together. We do that in one step. So here we have negative h plus rh plus 2h. Well, we can't do much with the rh because we don't know what r is. but the 2h and the negative h combine to make simply h plus RH. And if we pull out the h, that leaves us with h times 1 plus r, h times the quantity 1 plus r, all over 1 minus r. And that can be expressed like this. So our formula looks like this. And that's a very interesting result. So we can take the initial height and multiply it by the ratio of 1 plus the common ratio over 1 minus the common ratio. So let's take that formula and put it into our example that we were looking at earlier. Okay, so we start with our formula. Here are the values. We start at 16 meters, and the common ratio is 1/2, so it's bouncing up 1/2 each time. So plugging in the numbers into the formula, we have 16 meters times 1 plus 1/2 over 1 minus 1/2. Well, that's equal to 16 meters times, well, 1 plus 1/2 is the same thing as 2 over 2 plus 1 over 2, which would be 3 over 2. And then 1 minus 1/2 is 2 over 2 minus 1 over 2, which is 1/2. Now when you have a fraction divided by a fraction, you take the denominator, the bottom fraction, you flip it, or take the reciprocal of it, and multiply it by the top fraction. Like that. And in this particular example, you'll notice that we have a 2 in the top and a 2 in the bottom. Those can divide out and equal 1, or sometimes we say we cancel out the 2's. And that leaves us with 16 times 3, 16 meters times 3, which, of course, is 48 meters. And that's the trend that we saw on our spreadsheet, our experiment, if you will. So let's do one more example just to see something interesting. There's our formula. And let's start now with a height that's lower than our previous one. This one's 10 meters instead of 16 meters. But we're going to make our common ratio 3/4 instead of 1/2. The question is, how do you think the total distance traveled by the ball will compare to the previous example? Will it be the same? Will it be more? Will it be less? So let's plug in the values and find out. So here's the equation with the numbers plugged in. The total distance is 10 times 1 plus 3/4 divided by 1 minus 3/4. Well, 1 plus 3/4 is 4 over 4 plus 3 over 4, or 7 over 4. And 1 minus 3/4 is 4 over 4 minus 3/4, which is 1/4. Again, we flip and multiply. The 4's cancel out, leaving us with 10 times 7, and that's 70 meters. So that's an interesting result because although we started at a lower height for our initial drop, the common ratio was greater, so it's bouncing up 3/4 each time. Again, that may certainly not be realistic, but it's an interesting result. So you might want to try it for yourself with, something like 1/5 or 1/10, and see what you would get. So to recap, as long as there's a perfectly elastic bounce, and by that I mean that there's no energy loss to friction when it hits the surface, or air resistance as it's falling, or internal heating when the molecules of the ball rub against each other on the inside, or anything like that, then, and the bounce is some fraction between 0 and 1 of the previous height, an infinitely bouncing ball, something that's bouncing up and down an infinite number of times, in other words, it's bouncing forever, will travel a finite distance, and that finite distance is defined by this formula. Isn't that interesting? Well, I thank you for watching, and I hope you enjoyed this presentation.